All right, so today I want to talk about hypothesis testing. Again, this is stuff I know you've dealt with in 2126. We're going to deal with it again. We need three things to say there is a causal relationship, and really, we really care about that. We want to say that X causes Y. That's an important thing to us. As scientists, we want to say that under certain conditions, X causes Y. You need temporal precedence. X has to come before Y. X can't cause something if it happens after Y. Right? That's impossible. That's not how our universe works. So for a cause to happen, it has to come before the effect. We have to eliminate alternative explanations. Right? To eliminate alternative explanations. So to make sure that there's not some other variable, it's not that X causes Y, it's that actually Z causes Y. But we just need to do a very good job designing our experiments. Finally, we have to say there's covariation, such that as X changes, Y changes in some systematic fashion. Now, it could be systematically goes up and down. It could be two groups go up and one group goes down. It doesn't matter, but there has to be some covariation, right? This is stuff you would have dealt with in the research methods class in 2127. At least it was last time I taught it, which was 1997. I'm so pleased that I've never taught it again. Because I actually fell asleep lecturing one day. It was so boring. Find that stuff to be just... I mean, it's important. You have to know it. It's good. It's all valuable, and I hate it. It's so boring. That's all. Whereas this stuff I love, which I know makes me seem very odd. These first two, temporal precedence and elimination of alternative explanations, you deal with those through design. Right? So if you design an experiment properly, I mean, it's hard to design an experiment such that the cause would come after the effect, and that wouldn't be that weird. But elimination of alternative explanations, that's something we care about, right? How do we typically deal with elimination of alternative explanations? What's the most basic thing we do in psychology, typically, to deal with this kind of thing? Randomly assign subjects to groups, right? Just randomization. It just means that all the other characteristics of the groups are randomly assigned, basically, because we've assigned subjects randomly to groups. Okay? The third one isn't through design. Covariation isn't through design. We deal with that. We find that out by doing statistical tests. Right? So I made up some data. It doesn't matter. Don't worry about copying these freaking down. They're just numbers. Go ahead. You want to copy down numbers? You like copying down numbers? Go nuts. In the words of Principal Skinner on The Simpsons, science has all the excitement of sitting still, paying attention, and writing down numbers. And believe me, that's true. So, fine. You want to write these down. But I got two groups here. One is a mean of 66.2. One is a mean of 71.6. Standard deviations, respectively, 7.85 and 8.56. So we have two groups here. I don't know what these are. They could be they could be set of test scores, I guess. I don't know. Looks like it. Could be. So they're just some made-up numbers. Okay. So here's the question you want to ask. Here's a distribution with a mean of 72 and a standard deviation, I think, of 8. I think so. Over there. Smaller. Could those two sets of scores, those two groups of scores, so those two batches of numbers, could they have come from this distribution? So I'm saying theoretically, hypothetically, this is a population distribution. Hypothetically. I'm not saying it is. I'm saying, let's pretend. We don't normally know this. I said that the other day. We don't normally know population distributions. We don't know means. We don't know standard deviations. Let's pretend we do. So could those two batches of scores come from that distribution? That's the question. One was around 66, one was around 72, right? Well, if one's around 60, it's right here. It seems pretty likely. This is the probability of getting a score of that size. The other one's 72, that's right in the middle. It seems pretty likely to me that those two sets of scores come from that distribution. Now, I'm not saying we ever know this in advance, because we don't. But as a thought experiment, do you see why I'm saying that those two batches of scores come from, or could come from that distribution, assuming we knew it in advance, which we normally don't, or never do? Does that make sense to everyone? Okay? So it makes sense, right? It's possible. We don't know this typically, hardly ever. And again, if we know the population data, why do we do the science? There's no reason to do it. We already know it. But hypothetical. So what we just did is intuitively make a decision. We've said the chance is big enough that they come from that same distribution that we wouldn't be confident saying that those two batches of scores come from different distributions. They come from the same population distribution. We did it completely intuitively. We didn't do any arithmetic. We didn't do any math. It's not based on any math, really. It's based on just intuition and looking at something. So it's an intuitive feel for us. So it's not just, she said, just intuition. If the chance of those two two batches of scores coming from that same distribution is relatively small, and there's a convention, we say usually less than a 5% chance, we make a decision saying that they don't come from the same distribution. If they don't come from the same distribution, they by definition come from different distributions, yes? And that means we have an effect of the variable we've changed, the independent variable. Okay? And we say it's statistically significant. And then we publish articles and get tenure. So we say the effect is statistically significant if there's less than a 5% chance. As a rule, we use 5%. There's our worship of the 5% level of significance, which is stupid, but that's beside the point, and we'll talk about that shortly. So without the statistical significance, we can't confidently say we have covariation of x and y, and if we don't say that, then we can't say that x causes y. That's why this part, the statistical part, is just as important, or perhaps more important, depending on your point of view, I guess, as the design part of things. Okay? Do you see the logic behind this? Am I making a compelling case? Any questions? Does this make sense so far? Okay, good. So what we tend to do is we set up two mutually exclusive hypotheses. We set up HO, the null hypothesis. Sometimes people say H sub O. There was a time before this became a term, people used to say ho. It's not something people say anymore. But seriously, people used to say ho. Ho and ha. No one says that. So H sub 0 or H0 is the null hypothesis. And HA or ha, sometimes H1 or H sub 1, you'll see that terminology used to, any of those are fine. That's the alternative hypothesis. So the null hypothesis is that there is no difference between the two groups. or however many, let's just use 2 for now, doesn't matter, that there is no effect of the independent variable, that the 2 batches of scores come from the same distribution. All those things I said mean exactly the same thing. I'm being redundant. I'm repeating myself. I'm saying things over and over again. The alternative hypothesis just says, nope, not true. That's all it is. It doesn't say anything about how the distributions differ. The parent population distribution says nothing about that. It just says they are different. Okay. Question so far. Does this make sense? Does the logic of this make sense so far? Good. So we can actually set up this sort of matrix. Whoa, I know jujitsu. Is it a matrix reference? Thanks, where you home? And talk about how we can make mistakes. Up here, along the top, we have reality. HO is true or HA is true. They can't both be true, they can't both be false. Okay? So HO is true or HA is true. But see, we don't know reality. We don't know this because if we knew it, we wouldn't have to do the experiment, right? So we don't know if they come from 2 different distributions. We just don't know. But we accept that there is a reality out there. We just don't know it. There's no reality, man. Objectivity is subjective. Shut up. Get out of here. Sure, there's a reality out there. The question is, can we see it? And we can't. Can we make some guesses about it? That we can do. Here's one guess we can make. Let's not reject HO. So let's say that they come from the same distribution, that there is no effect of the independent variable. Those again, both being the same thing. If this is true, we do not reject HO. And if HO is true, we've made the correct decision. It's a boring decision that doesn't get anybody anything exciting, but at least we didn't make a stupid mistake. We didn't say, there are no psychics. Sorry, we said there are no psychics and there are no psychics. So we didn't say anything stupid. That's not going to be a groundbreaking paper. You're not going to get anything in Nature saying there aren't any psychics. But at least you didn't make an ass of yourself like you could, perhaps here. You could make a mistake. And it's going to happen. When we say there's only a, for example, 5% chance that HO is true, that means 1 time out of 20. We're going to do say something stupid. This is why we have to replicate things. Because if it happened by dumb luck, if it actually is the case, there is no effect that HO is true. But we come to the conclusion that we reject HO. We've made a mistake. We'll do the experiment again. Do the damn experiment. Make sure when you go to say there are psychics and you try to get that published that you've replicated it. And I think probably more than once. So we actually know the probability of making what's called a type 1 error. We said it. We say, let's say, and typically we say 5%. There's a 5% chance. What if HA is true? What if ha is actually true? We could miss it. We could not reject HO. Even though HA is true, we go HA is true. We're going to miss it. Never mind. We're going to make mistakes. we're going to make, in this case, what's called a type 2 error. So a type 1 error, the probability of making a type 1 error is alpha, and we set alpha, 0.05 or whatever. We set that. That's our business. The probability of a type 2 error is beta. So we've got probability, type 1 error, whoops, error, is alpha. Probability of type 2 is beta. I will apologize in advance that we're going to use alpha and beta for all kinds of other things too. Sorry. It's not my fault. It's convention, okay? So don't get mad at me. We could miss something. We could miss something exciting, but at least, well, somebody else will find it. That's screwed. So we could make a correct decision here. HA is true, and we reject HO. We've made a correct decision. That's what's called our statistical power. The probability of making a correct rejection of a false null hypothesis is 1 minus beta, and it's called statistical power. So the probability of rejecting a false null hypothesis, that's what power is. We made a correct decision. Note a couple of things. I've not once said accept HO. I've not once said accept HA. We reject HO or we don't reject HO. We don't accept things. Those are two different things. It may seem like a distinction without a difference, but it's not. Questions so far? This is stuff I'm sure you've seen before.
Can I ask why?
Please.
You don't say it.
Because it's basically, given the evidence we have, we don't reject something. It doesn't mean, in fact, just because we didn't reject something doesn't mean that it's true. We don't know reality.
Okay.
Right?
So we're accepting, or we're stating sort of that it's an assumption?
No. The assumption, the base assumption of all inferential statistics is there is no effect of the independent variable. All the math is based on there being no effect of the independent variable.
So fail to reject, right?
Yeah, so you fail to reject. You say, well, I don't reject, or I do reject. We never
because
accept.
We don't know reality. We're making.
We can't. Yeah, we can't.
Inference, right?
Yeah. So what we're doing is we're basically, it's kind of like in a court of law. They never found innocent. We found not guilty. Right? We found not guilty. So if HO is true, and we don't reject HO, we've made a correct decision. A boring one, but we've made one that doesn't make a fool of ourselves. On the other hand, if HO is true but we reject HO, we've made a mistake. We've made what's called a type 1 error. The difference between the type 1 error and the type 2 error, besides the fact they're different things, is that we know the probability of making a type 1 error. We set that in advance, 0.05 or whatever we're using. If HA is true, but we fail to reject HO, we get a type 2 error. But the probability of that is beta. And we don't know what that is.
At all?
We can estimate it, and it will be a class. Perhaps, I think that's next Thursday. There are ways to estimate these things.
They're not really necessary.
Oh, they're necessary. Not enough people do them. Because if I can say, what's the probability of making a correct decision, I want that to be high. I want 1 minus beta to be high.
So 95.
Yeah. Well, I don't think it's never going to be 95. You're going to get something. Well, you might.
Well, wouldn't you hope for that, seeing as the last?
No, you'd hope for something like, if you got like 0.7, you're rocking. Yeah. So 7 times out of 10, if there's no effect and you make the correct decision, you're in pretty good shape. All right. Questions so far? Good? Okay. So again, correct decision, type 1 error, type 2 error, other correct decision. The correct decision we tend to want is this one down here. HA true, reject HO. We'd like that. We design our experiments hoping that those things are true. Okay. So we have some control over the error probabilities. We set the probability of a type 1 error, and we usually set it at 0.05. This is a convention that I think is stupid. And I'll go into why in a moment. But this is noted is called alpha, the probability of type 1 error. The probability of type 2 error depends on n, the number of subjects, sigma, the population standard deviation. Think about, remember going back to that, could have come from this distribution. If that distribution was much tighter, instead of having a standard deviation of 8, had like 1.5, or it was really tight, we'd say they came from just different distributions. And alpha. The bigger the alpha, the more likely we are to say there's an effect. The problem is, if we start saying alpha is 0.25, we then say we have a 25% chance of making a type 1 error. We don't really want that. There may be cases where we're okay with that. And that's called beta. And 1 minus beta, a correct rejection. That's power. All right. What should you set alpha at? Well, everybody go 0.05. Because you've been taught 0.05. On your books it's 0.05. And all your papers use 0.05. What's magic about 1 time out of 20? Is there something magic about it? Is it something that makes you very comfortable?
19 is pretty good.
Well, it's interesting that, here's a little thought experiment. I've got a coin, if I had a coin in my pocket, and I flipped it 10 times. How many heads do you expect to get? 5, right? If I flip the coin 10 times and got 6 heads, who thinks I've got a fixed coin? Yeah, nobody. It could happen just by random chance. What about 7 times? It wouldn't surprise anybody, right? 7 times out of 10. What about 8 times? You start thinking I've got a fixed coin at 8?
Mm-hmm. Maybe.
Yeah? Who thinks at 8 I got a fixed coin?
Maybe.
Yeah? No? There's no maybe. It's yes or no?
Yes.
Okay, so we got one person saying it. What about 9? Do I have a fixed coin at 9? Madison also now is in on the train. At 10, do I have a fixed coin?
Yes.
Yeah, everybody says that, I hope. It's interesting that when you ask people and then instead of just sitting there blankly staring, they actually answer this question. Typically people put their hands up around 8 out of 10, which interestingly enough, when you do the math, is right around 95% chance. So for some reason it has an intuitive appeal to humans. I don't know why, but it does. This is all because of one man, R.A. Fisher. One man decided that 0.05 would be a sensible place to draw that line. R.A. Fisher, by the way, there's a reason it's called an F test, the analysis of variance, because it's named after Fisher. He invented it. He also came up with, those of you who have any biological background, the first kin selection model. I mean, this R.A. Fisher was a really smart man. And apparently, he had graduate students working on the percentages of the F distribution. You know, when you look it up, you know the F. And John Tukey, we talked about Tukey and exploratory data analysis. Apparently, Tukey gets in contact with Fisher and says, what percentage points are your students working on? I'll have my students work on the same thing. Remember, they're doing these all by hand, by the way. They're doing calculus. And Fisher replies 0.05. And Tukey goes, good, I'll have mine do some 0.05s too, so we can work together. And that's why we use 0.05. Because two guys decided it seemed okay. There's no other reason.
It's never been challenged?
Oh, it gets challenged more and more in the literature all the time.
Because I know that if you're doing like a pharmaceutical or a medical one, you go 0.01.
You might. This would really depend, right? So, I mean, you might want to be more flexible. In fact, I think we ought to be more flexible. So, I once got, this is literally, the reason that's a quote is it's a quote from a person who I will not name because I don't think it's fair to name the person. But an editor of a journal once sent me a review of a paper I wrote where all the effects went in the same direction, exactly what I hypothesized. And one of them didn't hit 0.05, and I noted that it was 0.0504. And I was told not to discuss non-significant effects. After punching a couple of walls and smoking a pack of cigarettes, I was a younger man, I realized, is this a hill I want to die on? No. If anyone takes a look at this, they will see that the effect, even though it's not significant, goes in the direction of every single other effect that I hypothesized would happen. Anybody will figure this out. I will talk about it. Fine. It's funny, at one point in that same paper, there were 4 alternatives that the animal had to do. Okay, 4 different alternatives. If the animal's responding at random chance, what should it be? 1 out of 4, right? So I compared the scores to random chance to 25%. And I got this reply from an editor saying, surely chance is 50%. And I replied, it's 25%, and please stop calling me Shirley. Sometimes one must quote Airplane. So I was told, don't discuss these non-significant effects. Now let's think about this. When would we want, and I heard this, I think I had a notion here, when would we want to not use 0.05? When would we want to be a little more stringent?
People's lights are on the line?
Yeah.
It depends. How so? So I'm saying going from 0.05 to 0.01, for example.
Or if the medication is supposed to work on a cancer or a certain type of brain condition, you want to be certain that chance is not a large factor, no?
And you already have a medication that works. What if you don't have a medication that works?
Like a trial? Is that what you're saying?
Yeah, so it's a clinical trial. You don't have something that works. It's a brand new medication. It's going to treat with some horrible cancer, pancreatic cancer.
Well, you better be damn sure out here.
Yeah, but what if you have nothing right now that works? I'm not saying there's nothing for pancreatic cancer that works, but what if you have nothing that works? What if there's an off chance this works? In that case, maybe you want to go the other way. You say, how about 0.15? What if you're testing water, drinking water? When I lived in Newfoundland, every spring, literally every spring, there was a boil order, or as we call them there, a boil order, right? On the water because of giardia. Fever. You don't want giardia. It involves a lot of diarrhea. You really don't want it. And for old people and little kids, it can kill them. It literally can kill you. And literally, honestly, every single year, there was a boil order in the spring because a lot of snow runs down from the mountains. There's a lot of poop from animals in the water. And there can be a boil order. And then when you live there long enough, you've got a filtration system and didn't worry about boil orders. But in that case, I'm perfectly happy with them saying, yeah, we're setting it at 0.2. Oh, I'm inconvenienced a little bit by boiling my water. I'd rather have to boil my water for no reason rather than poop myself to death. Right? I'm perfectly happy there. On the other hand, what if I'm saying, for example, that I have evidence that there actually exist psychics, people that can read your mind. You better make that pretty damn small. 0.001 would be nice. There's been literally no evidence of this ever. So how about we be really conservative here? Like really conservative.
0.001.
Oh yeah, I'd go at least there. There's a thing called a Bayesian prior. What's your prior? Like, what do you think the probability actually is that there are psychics? It's probably 1 in a billion. I'd probably go with 0.000000001. I think that was enough of those. On the other hand, like I said, if it's about public health, this is interesting. Most of the research on secondhand smoke and does it actually hurt people never reaches 0.05. But you know what? What am I more concerned about? That people can smoke places, or that people don't get cancer who aren't smoking? I think I'll go with the people who don't have cancer, don't smoke, don't get the cancer so much. Yeah, I'll be happy with that. So as I said, a lot of times the individual studies about secondhand smoke didn't hit 0.05. And a lot of people originally said, well, it's not 0.05. And then other people said, yeah, but they all go in the same direction. It all goes in the same direction. It's always like 0.06, 0.07, 0.06, 0.08. It's like, yeah, okay. Are you willing to stake public health on this? Probably not. Probably fair to go, probably shouldn't smoke in public, out in the classroom, probably not good. You know, go outside. Question, Chris.
How do you actually decide when you're doing an experiment? Do you do it
practically? You just use 0.05 because people are jerks. But if you're applying something, I think you have a much stronger case.
But
if you're doing something,
is it realistically up to the experimenter to decide?
Well, there's sort of a new movement out there saying that what we should do is present the probabilities, present the alpha levels when we do it.
Separate calculations, you mean?
No, you just present the alpha levels. You just say the probability of this being a type 1 error is 0.06. The probability of this being a type 1 error is 0.09. The probability of this being a type 1 error is 0.01. And then you say, and then you can interpret it as you wish. You interpret it. You don't interpret it as strong when it's, say, 0.09 or 0.01.
How do you decide those alpha levels? You just arbitrarily choose them?
You wouldn't do that necessarily. When you do calculations, say a t-test, when you look it up, when you do the software, it'll actually tell you the probability that it's on that. Yeah. We have a cutoff of 0.05 because we worship that because we're idiots.
That's what I was asking.
Yeah, so instead of doing that, the software will give you an actual number.
Okay.
It'll say the probability of this being a type 1 error is 0.037. That's why I was able to say it was 0.0504.
Okay.
I did note in my reply that had I rounded, I could have used 0.05, but that I had some integrity. I hope that the editor was able to detect my sarcasm. So yeah, it's not an easy thing to do, and I have a real issue with people. Don't discuss non-significant effects. It's like, look, we're not curing cancer here. These aren't public health issues. It's like, do people remember words better if I'm doing this rather than this? All the data from before says that should happen. I've done a small change on this, and I get 0.06, and you say, well, don't discuss it. It's like, get a hold of yourself. What makes you so self-important? And those of us, I used to say younger people in the field, but now I'm in my 50s. Over the years, more and more of us have started to have come around to that idea. And this especially works nicely in talks. It doesn't work as well in published articles, but in a talk when they say, so that doesn't hit 0.05, but you can see everything goes in the same direction. The worst thing that happens is something called p-hacking, Where what people do is go, okay, so that means if I got 2 more subjects, I'll get 0.05. Run 2 more subjects. I hate that. I mean, I want to just beat people to death with statistics books when they do that. But I see why they do it. Because people are like, I'll discuss non-significant effects. That's my impression of someone who's annoying and petty. It's not anybody in particular. Okay?
What if you state it for what it is?
How do you mean?
Almost significant.
Yeah.
Can you do that?
People do. People say approaches significance.
So couldn't you just say like, here's the probability of this being a type 1 error, like you were saying?
Yeah, people do that, and that's
And then-
becoming more popular among journals that aren't APA journals.
Because under APA you're not allowed like
APA worships the 0.05 level like it's some sort of god.
No, I understand that.
Yeah.
Is there like a rule of thumb where if it's not significant, you can't even speak about it in your paper?
Yes.
Oh.
Yes, that's the problem. That's the issue here. I mean, it's a really
That's like
serious
a
thing.
format law or rule.
Yeah. And look, when the editor says, somebody once said to me, APA says to use 2 spaces after a period, but the journal says to use 1 space after the period, and I said the person then you put 1 space after the period. If the journal says draw a picture of a unicorn after every question mark, that's what you do. You want to get published, or you want to just sit there and go, 2 spaces is for evil people? You know? It's like, just do what you're told. But it's an issue here. It's becoming less of an issue, but the problem is most of us who have a sophisticated statistical knowledge aren't listened to very closely. Oh, those are just stats people. Those stats people. So, yeah, you mean the people that teach you all how to use tools that you don't know how to use? I may be a little bit cynical. Just a little. Just a touch. Just a tad. All right. Questions? Okay, it's okay. Good place to stop, right? And we'll talk more next time. Thanks, everyone.